So please join the community and follow us. There's the link at the bottom. The beacons.ai will show you all of our relevant links, and you can follow us on LinkedIn, Twitter, Instagram, and Facebook. Okie dokie, I'm going to stop sharing my screen, and the lovely Nimrita will take it from here.
Thanks, Seranya. I'll be sharing my screen, which is a Jupyter notebook, and just let me know that it's fine and everybody can see my screen, right? Great. So hi, everyone. I'm very excited to be, doing this session with you. Today, we are going to look at text classification in particular, and we'll have a bit of introduction to transformer models. Why? Because ChatGPT-3 and GPT-4 and all of those huge language models that are, about to disrupt our lives. So with that, let's get started. Here are the GitHub links to previous 2 sessions, and this session's Jupyter notebook is also available on my GitHub. We have already covered sessions 1 and 2. I'm doing a bit of recap on session 1. We introduced the field of NLP. We spoke about different tasks which involve in NLP. We then spoke about different applications, machine translation, autocorrect, question answering, conversational AI, and so on. We spoke about many libraries in Python, which help you do NLP with primary focus on NLTK and Spacey. In session 2, we provided ourselves with a recipe, a toolkit of different techniques for text pre-processing before feeding in our text to ML models. We also spoke about techniques like pause tagging, lemmatization, tokenization, stemming, removing stop words, and so on. And then we saw different techniques of converting text data into numerical vectors so that ML models can work with them. We covered one-hot encoding. We covered bag of words model with count vectorizer. We also saw TF-IDF. We saw application of word-to-vec, glove, and fast-tag ready-made embeddings, which can be used to convert our text to numerical vectors. In this session, we are going to look at some projects which do text classification. We'll have a look at what is text classification, what are the steps involved in classifying text, and then we'll see the code. Finally, we'll have an introduction to transformer models or large language models, which include models like BERT, GPT-3, 2, 3, 4, and so on. And here are some references. They are given as a part of Jupyter Notebook to you. You can go ahead and check them for detailed information about whatever we are going to speak today in this session. All right, so what is text classification? Classification means to group or label something, right, into predefined categories. So essentially, text classification is about finding out the category to which some piece of text belongs. For example, whether an email is a piece of spam mail or is it a genuine mail you are interested in, you would like to have in your inbox. Whether a web page is somebody's personal homepage or whether it's a business page, whether a news article is talking about politics or economics or finance or entertainment, things like that. Whether a review comment given by a user on Amazon.com has a positive sentiment, is it speaking positively about the about customers' experience about the product, or a negative sentiment is carried by that review. So all these tasks are called as text classification. A news article, we pass this text of the news article to a classification model, and then the model tells us, to what category does this article belong to. Similarly, there is some email, we pass it to the classifier model, and then it tells us whether this mail is a spam or it's a genuine mail. And if it's spam, it should go to your spam folder. If it's a legible mail, if it's a mail which you would be interested in, so it should go to your inbox. So essentially, there are, just like for ML programs, ML projects, we identify certain features from the input data, and then we train the model on those features. For text also, we identify certain features of the text, which we provide, which we feed into the ML model on priority. Some features, some special words or some special patterns in the emails, for example, can identify those emails, can help the classify model to identify those emails as fake or phishing emails or spam emails. Here in this figure, we are looking at some examples of what distinguishes a spam email or phishing email from a genuine one. So for example, here the email ID from which this mail is received is kind of fake. Like instead of being a genuine Microsoft email ID, a domain name is, it has some words which don't appear like to be a genuine Microsoft email ID. So there are kind of words which signify a threat. There are some spelling mistakes. There are some words, which are not grammatically correct. There are some punctuation marks which are not correctly placed according to grammar. Then your signature may not look very, nicely placed. And then there may be a lot of colors that are used in the text. There may be presence of certain words like which are offensive words related to lottery or, sexually, suggestive words or words like that. So all these words which we, with the naked eye also we identify as off-putting, we also can feed into an ML model, and then we can automate the task of classifying mails as spam and non-spam. On the similar principle, other text classification tasks also work. So they also try to identify the distinguishing features which separate a valid piece of text from a invalid piece of text, or the text which belongs to different kinds of categories. So for the task of text classification, we can use both supervised ML, supervised machine learning, as well as unsupervised machine learning. In this session, we are going to demo supervised machine learning. And in the session coming up next week, we will be looking at transform models and unsupervised machine learning for classification and some sentiment analysis. So in supervised learning, what we feed into an ML model is the labeled data set, which means there's a human annotator or a human expert who has labeled certain pieces of email as spam and certain other pieces as non-spam or as genuine mails. This labeled data set is fed into the ML model like a support vector machine or a logistic regression classifier or a deep neural network, and the model learns the patterns. It learns to associate a valid text, a non-spam email with the content and a spam email with the content. So these learned patterns or weights is called as training a model, or a fully trained model is a model which does very little, which does very few errors in classifying your text into the categories that it should belong to. So for any supervised learning task, a good quality labeled data is absolutely essential. And then often during the training process, we split this data into three portions: a training portion, a validation portion, and a testing portion. We find the patterns, or we train the model on the training data. And then we have a portion of data which is called validation set, which is used to fine tune our ML model. And then we have test portion of the set, which is used absolutely to make predictions and to judge the accuracy, judge the performance of your model. There are certain metrics which are used to evaluate the performance of our classifiers. Commonly used metrics are accuracy, precision, recall, and FN score. So here we'll look at general flow of steps in almost all classification problems. This is specific to text classification, but general classification also follows more or less the same steps. So we have a text corpus, which is a huge collection of text data. It can include multiple files. It can include data coming from a publicly available website like Wikipedia, or data collected by web scraping, or through the websites like Common Crawl. All this data is first analyzed, which is called exploratory data analysis. What kind of data is there? What are the features? Like, are there too many digits? Are there any hashtags? Are there any special symbols? Or are there any spelling mistakes? Based on what kind of data you have, you decide what kind of pre-processing we need to do on it. For example, we will convert all the text into lowercase, then we will remove the stop words. We have seen how to do this previously in the last session. We will, for example, remove all hashtags if you are working with tweets. We'll also remove all the mentions. We may decide to anonymize our text, remove all the mentions of people, or all named entities like the names of places or names of companies. We may decide to do this depending on what kind of task, what kind of project you are working on. So after this pre-processing or cleaning of your data, we go ahead and convert the text into numerical vector representations, because by now we know that our ML models cannot work with text, and they only work with numbers. So there are certain rules regarding what kind of, what to do, like how to convert our text into vectors. There's a general rule. If the number of samples to number of words per sample ratio is less than 1500, number of samples means how much text you have, how many documents you have, how many sentences you have. And number of words per sample means in one sentence or in one document, how many words you have. It's a generally accepted rule of thumb. If this ratio is less than 1500, then we can tokenize our text in the form of n-grams. Again, I'm referring to the previous session. N-grams do not preserve the order in which text is available or text is fed to the model. We split the word into n-grams. We convert those n-grams into numerical representations using either TF-IDF or count vectorizer or one-hot encoding. And then we pass these vectors on to the ML model for training. If the ratio of number of samples to the number of words per sample is above 1500, we then use sequences. We convert the input sentences into sequences of vectors. And then when we have done the conversion into numeric vector forms, we select, let's say, top 20K vectors for training into the training our ML model. This is not a hard and fast rule, but this is the generally accepted rule of thumb in the NLP projects. So once we figure out what kind of embedding to use, whether we have to go with n-gram model or to use sequence model, we begin with finalizing our features or selecting or extracting our features. Also, if the ratio of number of samples to number of words per samples is, well above 1500 but below 15,000, in that case, we can also go ahead and use a pre-trained embedding like Glove or Word2Vec, and we can fine tune it with our own specific words or depending on the specific data set or specific language of that data set that you are working with. So once we have done the feature conversion or once we have done the vector embedding of our data, we can go ahead and decide how many important features are you going to use to train your model. This can be done by a statistical procedure like finding chi-square values of the features with the class labels or using F-score values of the class or the features with your class labels. So generally accepted rule of thumb is that we can go ahead with 20,000 features. And how many features work best for you, it again depends on the project you are working with. It may happen that you have a huge amount of text and 20K features just don't give you a good enough accuracy. In that case, you can decide to go ahead with more, or you can also decide to go ahead with lesser number of features if the corpus size is less, if you have lesser amount of data to begin with. So by now we have our text data, we have cleaned it, we have converted it into numerical forms, we have extracted the important pieces of text from it, important words or important features from it. The next step is to train your model. So training your model means learning the equations, learning the patterns between the text and the labels it has been given to by the human annotators or the labels that are present in the labeled data set. These models can be n-gram models if you have used n-grams to tokenize your text. The n-gram models generally include conventional ML algorithms like multi-layer perceptron, logistic regression, and so on. And these models do not consider the order relationships between the words. And then for longer sequences, we can use models like convolutional neural network, recurrent neural networks, LSTMs, bi-LSTMs, and so on, which also consider the information regarding neighborhood among the words or adjacency among the words. So what happens during the training of a model? The model looks at the data and it looks at the labels. It tries to predict the label for unseen data or for new row of the data. And then it does a comparison between the prediction it makes about the label and the label that is actually present in the data. Again, we remember that this is pre-labeled data, right? So the target labels are already there in the data set, in the training data. You try to predict the label and see whether your prediction matches the actual label. If it matches, you're great, you're doing well. If it doesn't match, you've made an error. So it counts all the number of all the errors it makes during a specific epoch of training. And the goal of your classifier is to reduce or minimize its errors to a minimum. This is something which is measured in the form of accuracy, which exactly means the number of correctly made predictions divided by total number of predictions your classifier makes into 100 if it's measured in terms of percentage. So again, for every classifier, there's a loss function which counts the number of mistakes your classifier makes. For example, for the classifiers which have two classes, we have binary cross entropy. For multi-class classifiers, we have cross entropy loss. For regression problems where we are predicting numbers, we have mean squared error loss function and so on. And also this training requires backpropagation, which means the value of your error function, or rather the derivative of your loss function is passed back from the last layer of your model backwards to the first layer. The weights of every node in your neural network are updated so that we reduce the error of the classifier in every iteration of backpropagation. This requires some kind of an optimizer algorithm. I'm sure pretty much some of us at least have heard about gradient descent or stochastic gradient descent, which is the algorithm used for optimizing the weights of a neural network during backpropagation. For tasks like text classification, we now use optimizers like EDAM or RMSprop or EDAProp. And then when we have done the training, we are looking at the accuracy, the performance of a model. We then can further do some hyperparameter tuning in order to improve the performance if you are not satisfied, or if there's a scope for improving the performance further. Hyperparameters are the parameters which are not learned during the training, like the weights of your neural network or weights of your classifier parameters will be learned during the training, but hyperparameters are not learned during the training, and you need to tune them by hit and trial, by trying and seeing the performance, trying again and finding out that sweet spot where your hyperparameters are perfect and your accuracy is very good, your loss is very less, and so on. Loss means the error rate. So what are these hyperparameters? How many layers you want if it's a deep neural network? How many nodes or neurons you want per layer? How many times you will be looking at the data, which is called the number of epochs? What will be the batch size? Means in one go, how many rows of data you'll be feeding into your model? Will you be stopping early? How much output size you want, and so on. So hopefully after all this hyperparameter tuning and your training, now your model is making very, very less errors and its performance is very good. This is the stage when we actually are ready to deploy our model. Deploy our model means you actually put it to use in production scenario where you have new data, new pieces of email, and you let your model decide whether this mail is a spam mail or a ham mail, a genuine mail. So what are the important use cases of text classification? It's used heavily in sentiment analysis, in spam, finding out spam filtering, then pause tagging. It's also used in natural language inference, which means identifying whether two pieces of text are actually speaking about the same thing, or can you infer second piece of text from the first piece of text, whether these two pieces of text are called a premise and a hypothesis. We see an example here. So here's a premise. I'm watching a movie right now, and the hypothesis, second piece of text, is that I'm playing cricket right now. Obviously, these two things cannot happen at the same time. So there's a contradiction between them. This label of the kind of relationship between these two pieces of text is contradiction here. There can also be entailment, which means both the pieces of text are actually saying the same thing. They're conveying the same information. So I'm watching a movie right now is the text one. Text two is some movie is playing in front of me. They essentially mean the same thing. So this is the type of relationship here is entailment, or they are supporting each other. There can also be a third category where there's no relationship at all between the two sentences. I'm watching a movie and my sister is playing football. So no relationship at all. Text classification can also be used for checking the correctness of a particular piece of text with respect to grammar. All right, so we're getting started with coding. We will first see how to implement, how to do text classification with NLTK libraries, built-in functionality. Then we'll see how to do it with sklearn library and the classifier built into it. Then we'll see how to do it with Keras. Okay, let's get started. So I hope we already are using Anaconda for doing all these, the practical work of all these sessions. On top of Anaconda, we have spoken about NLTK, Spacey, which should already be installed on your computers. If not, then please go ahead and install NLTK and Spacey. Once you are done installing, we need to import NLTK into our Jupyter Notebooks code cell. we need to download this movie_reviews dataset. This is a built-into text corpus, which is available with NLTK, but we need to get it into our Jupyter Notebooks workspace. So once you have done that, from nltk.corpus, we import the movie reviews dataset. This movie reviews dataset contains around 2000 text files. Every file contains a review given by some users about some movies. There are 1000 positive reviews and 1000 negative reviews. All the positive reviews are placed in a folder called POS, and all the negative reviews are placed in a folder called neg. Every file has a file name, which is called file ID in NLTK. So here is how you can see how many files you have. So length function helps you see the length of a list. File IDs is a built-in function which helps you to figure out all the file names in a particular text corpus. Movie reviews is a text corpus. We imported it from nltk.corpus. File IDs, and I'm checking the length of file IDs, which means how many file IDs are there. There are 2000 file IDs, and we are just printing first 5 file IDs here. In the neg folder, there's a file ID, called CV000_29416.txt and so on. So these are first 5 files. They are all in the neg folder. So that means they contain negative reviews. Again, we now separate positive file IDs into a variable called positive_file IDs, and another variable neg_file IDs contains all the file IDs which are in neg folder. Total their length is 2000. So 1000 files in negative folder, 1000 files in positive folder. Here is how you can see the file name of first positive file. The raw is the built-in function which helps you see all the text in a particular file. So I've not printed the output here because it was very long. The content was very long. But you can run this cell and see all the words that are present in the file ID 0, first file ID in positive reviews files. Words function again is a built-in function which helps you to tokenize the text and see every word individually for the file ID you are interested in. Then we separate into a variable called reviews with categories, all the reviews along with their categories. So this is where we are generating our labeled data. I have all the reviews from all the file IDs, and I have their categories also. The categories are coming from the corpus name.categories function, and the file IDs are coming from the corpus name.file IDs function. For every category, I'm getting the file name and the category name, and this list is being populated in this variable reviews with categories, right? We are just doing a random shuffle of this in order to ensure randomness in the content. So this is where we are getting labeled data, the reviews as well as the categories. Category essentially means the label negative or positive for the reviews. Doing a bit of text pre-processing here. So what kind of pre-processing we are doing? We are converting all the words to lowercase. We are removing the punctuation marks. We are removing the stop words, and we are removing the empty strings. We have covered this in detail in the previous session. So if some of you, have not been part of that session, I would request you to go ahead and check out the Jupyter Notebook and the video of that session. So after that, we are figuring out all the words in our all the reviews along with their categories, and we are putting them in a variable in a list called cleaned reviews. This cleaned reviews means all the text pre-processing has now been done on them. And then we figure out what is the frequency of all words in our text, or in the review text. Now, this can be done using the frequency distribution built-in function of NLTK. We pass it the list of all words, and it gives us a word-wise frequency distribution. This word, how many times does it occur? This word, how many times does it occur? And so on. We are printing the most frequent 10 words. Most frequent words mean the words which have highest occurrence frequency. So incidentally, because these are movie reviews, the words like film and movie and so on occur very frequently. Here we are identifying 5,000 most frequent words in these reviews. These most frequent reviews, most frequent words will be the features we'll be focusing on. We are not going to train our model with all the words, but only 5,000 words, which are very frequently occurring in our data. Based on these frequent words, we are writing a function which is extracting our features. What essentially this function is doing is trying to find out whether that frequent word is present in the given review or not. If the word is present, it just attaches a true to that word. If a word is not present in the specific review, it attaches a false to this. So it essentially is creating a Boolean value. It is associating a Boolean true or false with a word if it's present in the review or if it's not present in the reviews. And all these words are only the words which are frequent, which are 5,000 most frequent words. We apply this extract function, extract the frequent word feature function or all the reviews. Here I'm printing just the review one, the features of review one. So for all the words which are in review one, we are getting a feature like this. Movie word is present, so it has a true associated with it. Concepts is present, it has a true. There are certain words which are not present in this reviews, but which are frequent words. With them, we have associated false like this. These are the frequent words in overall text corpus, but these are not present in this review, the first review. So a false is associated with them. Now this is our feature vector. Feature vector means the word and whether it's present or not. Along with this feature vector, we also have the final label of the data, final label of the review, which is negative in this particular case. Then, as I spoke about this earlier, every classification task which uses labeled data prefers the data to be split into test and training portions, test portion, training portion, or a validation portion, at least a training portion and a test portion. So out of our 2000 reviews, we are taking first 1800 reviews in the training portion and remaining 200 reviews in the test portion, which is called test underscore data. We are training the built-in Naive classifier of NLTK using trained data. The name of this NLTK classifier is CLF underscore NB. In this case, this is a user-defined variable name. You can use any name. Just look at the classifier. This is a built-in algorithm in NLTK library, and we are calling it using NLTK.Naive classifier, calling the train function on it. We are training it on the trained data, which is nothing but your first 1800 reviews. Then we can evaluate its accuracy, which can be done simply by calling the accuracy function nltk.classify.accuracy. You pass it the classifier object and you pass it the test data. So basically during training, your classifier object has figured out the relationship between data and the labels, and it can make predictions regarding all the test rows, the reviews in the test data, and then compares those predicted labels with actual labels in the test data. And incidentally, our accuracy in this case is 75%. 0.75 accuracy means it is 75%. You can multiply it with 100 on your own. And then we can see what features were considered most informative by our classifier. So here's the output. These are 10 most important features. The word breathtaking, whenever it was present, it was a very informative feature, and it was present 12.6 times more in positive reviews as compared to negative reviews. Similarly, this word insulting was present in negative reviews around 9.8 times more as compared to positive reviews. So this insulting is a negative feature. It signifies a negative review, and breathtaking signifies a positive review, and so on. So I'm going to move to sklearn for classification now. Are there any questions which we can take right now? Is it possible set the GitHub link? Okay.
Yeah, we will get those to
Yeah,
you, but
yeah.
it doesn't look like any questions just yet.
Yeah, sure. So we'll go ahead and cover classification using sklearn. Sklearn is a very well used library for ML tasks in general, and it also has a very good support for text classification and text data preprocessing. So for that, we import sklearn classifier object from nltk.classify.sklearn. We also import the algorithms, logistic regression, multinomial naive, spot vector classifier, k-nearest neighbor classifier, decision tree, and random forest. These are the classifiers we'll be using to fit a model, and then we'll compare how they do with our data set. For doing this, we create a list of names of classifiers and a list of actual algorithms of the classifiers. We zip them together, and then in this for loop, we are training every one of our models one by one. What are we training on? We are training on train underscore data, and we just saw train underscore data is our first 1800 reviews, and test data is the remaining 200 reviews. In all, we have 2000 reviews in our data set. So once we train on our training data, your model has learned the labels, has learned the patterns or relationships between the text and its label. It's now ready to make predictions, and we can evaluate its accuracy using the built-in function accuracy, which comes in nltk.classify. You pass it the trained classifier, you also pass it the test data, and we can print the accuracy here along with the name of the model. We can also see the predicted values that are created by your classifier. We can also see the detailed classification report, which shows you the precision, recall, F-score, support, all the metrics that we use for evaluating the performance of a classifier. We can also print the confusion matrix, which shows us class-wise. If there are 2 classes in your text, then how many errors were made in class 1, how many errors were made in class 2. If there are multiple classes, we can see for every individual class how many labels were correctly predicted and how many errors were there. So I'll not be getting into details of the format of confusion matrix and all. My intention here was to let you know that we can produce all of this directly from NLTK's built-in classifiers and directly from sklearn's classification model algorithms also. So for the first classifier, which is logistic regression, we are getting around 82.5% accuracy, and our precision recall for positive and negative classes is around 83%. The confusion matrix is something like this, which shows on the side of your index, the actual values, on the side of your columns, the predicted values for class 1, for class 2, for class 1, for class 2. So there are 80 values of class 1, which are predicted also as spam and which are actually also spam. So the diagonal entries should be maximum in a confusion matrix. Similarly, for multinomial naive Bayes, we see an accuracy of around 84%. For support vector machines, it's getting 80%, which is lesser. For KNN, we see a very, very less accuracy of around 50.5%. Again, for DT, for the decision tree classifier, it's 62%. For random forest, we have slightly better than DT. All right, so next we are moving to a deep neural network, which is implemented through Keras. For this example, we are using the labeled sentences downloaded from UCI Irwin's repository. This is Amazon reviews, the product reviews from Amazon. This is in the form of a text file, so I'll be using pandas here to read this data set. We have imported pandas as PD. We are using read_CSV function to read our file, which contains the Amazon reviews along with their labels. The file name is amazon_cells.label.txt. You can find the data set here in the link shared here. It's a publicly available data set. The column names I want to give to 2 columns in this data set are the sentence and its label. So this is what the data, first 5 rows of our data look like. There's a column containing sentence, and there's a column which contains the score or label of that sentence. 0 means it's a negative review. 1 means it's a positive review. So if I just want to look at first column, I can do that using the name of data frame and using bracket operator to just extract 1 column of it. So this is what my text looks like. Then, as usual, we'll do some text pre-processing on this data. We are removing all non-ASCII characters. We are removing anything which begins with a digit. We are removing the punctuation marks, converting to lowercase, removing the stop words, lemmatizing all the words, and this is the pre-processing we do on this data set. After the pre-processing is applied to all the rows, all the reviews in my data set, this is the data that is left. So all the stop words have been removed, all non-ASCII characters have been removed, and so on. Now this is our cleaned pre-processed data. I have taken the sentences column in a different variable called sentences, and the label or score column or the sentiment column in a variable called labels. Then we do a train test split. In sklearn, there's a train test split function which divides your data, both the train data and both the columns or features and the labels into training and test portions. You can specify what portion you want in the test data, what portion you want in the training data, and so on. So sentences contain all the text, labels contain all the labels which are already present in the data. This is labeled data, right? Supervised classification. The output of train test split is 4 data sets: the training portion of your text, the test portion of your text, the training portion of your labels, and the test portion of your labels. Then the step is to convert our text into numerical form for feeding into an ML model. That in this case, we are doing with count vectorizer using a bag of words model. We import count vectorizer from sklearn, fit it to our training sentences, then use this fitted model to convert our training data as well as test data into numbers or into a vector form. After this, we will build the model, will fit the model. We are fitting logistic regression model first. We import it from sklearn, fit it on training data and the label data. See, this is the training portion of sentences and the training portion of labels. Let's pay attention to this part. This is not the data in text format, but the vector forms of our data, because your models cannot work with text. You have to pass the numbers to them. Once we have fit our logistic regression model on the vector forms of training sentences and the labels, we can use it to predict a score, or we can use it to make predictions regarding the labels of test data. We can use it, we can evaluate its frequency, its accuracy using the score function, which needs you to pass the vector forms of test data and the actual labels of test data from the data set. So incidentally, we measure the accuracy as 79% here. This is multinomial naive Bayes. Naive Bayes is the probabilistic algorithm we use to make predictions based on the probability of occurrence of a word in a sentence. So we import again sklearn, from sklearn, we import multinomial NB, create its object, fit it on training data and the training labels, and then evaluate its score or evaluate its performance on the test data and the test labels. So this is a slightly lesser than logistic regression, and it's around 74%. For the same data set, now we are going to use a deep neural network from Keras to do the classification. For doing that, we should have TensorFlow installed and Keras installed, the Python frameworks which help you do deep learning, which help you to build deep learning models like simple feed-forward neural network or CNN or RNN. So we have already our data set. We will use the built-in tokenizer of Keras to convert it into numbers. So I have imported tokenizer module from sklearn.preprocessing. We are fitting it on our sentences. This is DF sentence, the original column of our data set, which has not yet been converted into numbers. The tokenizer module automatically has the purpose of converting your text into numbers. Then we separate, we just take the sentences and labels in two different variables. It's a convention that we take features in X and the labels in Y. So that's what we have done here, taken all the features or text in X and taken all the labels in Y, using train test split function to separate our data into training portions and test portions. Similarly, we're separating labels into training portions and test portions. Once we have done that, we have already fitted our tokenizer here on the sentences, on our text. We are then using this fitted model to convert your training portion into vectors and your test portion of sentences also into vectors. Once this fitting is done, we can see the size of vocabulary. The vocabulary means how many unique words are there in your text. In this case, this is given by tokenizer's word index feature, word index attribute. We add 1 because this tokenizer dictionary starts indexing the values at 1, and overall length will need to be added 1 to in order to find the overall number of overall size of vocabulary. So in this set of in this text file, we have 1626 unique words. Here's an example. We have these 4 words, and using the tokenizer, you can actually see what numbers it has given to these 4 words. And then we can see the sentence length can be different. There can be sentences of different lengths, and it's generally accepted practice that your ML model works with same length of input. So we do padding and convert all the input sentences into the same length. This is done using pad_sequences module from Keras_preprocessing. We have decided that all the input sentences will be of maximum length 50. You can do this by using pad sequences function, applying it to xtrain, and also applying it to xtest. So now all your data, all your input sentences or sequences are padded with zeros to make them of same length. Let us say 50 in this case. After this, we are going to build our model. For that, we use Keras, and we are importing the sequential model from Keras, which means we are building a simple feed-forward neural network. And there are some parameters we need to configure for our model. For example, the embedding dimension, what should be the size of embedding that it creates for us? What is the maximum length of input that we are feeding into it? And what kind of model it is going to be? So it's a feed-forward neural network, which is signified by sequential. The first layer we add to the model is an embedding layer. Embedding layer's job is to convert your text into numerical vectors. So here we specify the input size, input dimension, which means how many unique words are there in your text. Output dimension, which means what should be the size of embedding that it creates for you, and what is the size of each input sequence, which is 50 in this case. And then we add a global pooling layer to it, global max pooling layer to it, which essentially converts the outputs into a single size, takes the maximum value from all the neighboring values of data and converts them into a single value. And we are finally adding, we are then adding a hidden layer, which contains 15 units, and each unit uses the activation function ReLU. Finally, we are adding an output layer, which is a dense layer with a single output neuron and uses the activation function sigmoid. Once we have decided the structure or architecture of our neural network, we can compile it. We are specifying what kind of optimizing algorithm to use, what is the loss function to be used, and in what forms we want to evaluate the performance of this model. So in this case, we'll be using Adam optimizer, cross entropy loss, binary because it's a 2-class classification, and we'll be measuring the performance in terms of accuracy. Here is the summary of your what your model looks like. It has first layer, which is an embedding layer. Then it has a global max pooling layer. Then it has one hidden layer, which contains 15 nodes. And finally, it has one layer, which is the output layer. There are in all around 164,000 parameters, which will be trained in this deep neural network. Here's the code for plotting the validation and train accuracy. So in this case, a model has performed reasonably well, around 99.7% accuracy on the training data, but this accuracy has come down to 77% in case of validation, which essentially means that the model is overfitting, the text is too less, we should increase the amount of text, or we should increase the amount of the number of epochs that a model is doing on the text, on the data. All right. So are there any questions here? Because then we are moving to transformers very quickly.
Yes, we have a few questions.
Yes.
The first one might be from the previous one. Was in the example hatred classified as a positive review?
In this example, let us go back and check. You are speaking about the most informative words we saw, I guess, right? Yeah. So here hatred is true. Yeah, incidentally, this is strange. It is found to exist 10 times more in positive reviews as compared to negative reviews. So yes, this model is treating hatred as a feature of positive reviews. So if it finds the word hatred in positive reviews, it has a 10% more, it has 10 times more chances of labeling that tweet or that review as positive. Yes.
Now, the next question by Kamshad is, for example, when I do sentiment analysis of movie reviews, I'm using Stanford Movie Review dataset, which has both training and test data separately. After I do the training and testing, I have to load my own dataset. Because this is a master's thesis, I always thought that I just use Stanford dataset.
You can go ahead with only Stanford dataset, and it's fine. If I don't know exactly what your thesis is focusing on. If it's just classification, then demonstrating it on the publicly available Stanford dataset is fine. But if your statement of, if your thesis statement is specific to a specific kind of dataset, then yes, you have to implement it. You have to demonstrate your proposed model on your dataset also. Yes.
Perfect. And then Undine said, for training, the classes should be balanced. Which effects are seen when in production one class is really rare?
Yes. Your training data should have a balance of all kinds of classes. If in case your classes are imbalanced, which means out of, let us say, out of 100 rows, you have 80 rows which are positive and only 20 rows which are labeled as negative, then your model is biased towards positive labels, right? In most of the cases, in most of the new data, it will, it has 80% more chance of classifying them as positive. So the balance in input data, balance of classes in input data is very, very critical.
And then we have the next one. How is the maximum decided? What criteria is used to help in determining the value, or is it arbitrary?
Value of max length, right? It depends on what is the average size of your sentences in the input data. Yes.
Perfect.
If your sentences are very short, you can go for a smaller value of max length. But if you see sentences, let's say 100 words long, which is rare, but let's say if it's there, then your max length has to be decided accordingly. Maybe the length of your longest sentence.
Awesome. That got all our questions answered. We can move to the third example.
Great. We covered third example. I think we covered doing it with NLTK. We covered doing it with sklearn's classifiers. We covered doing it with Keras, right? We will be moving to transformer models. Shall we?
Yes. So if anyone's heard ChatGPT, there you go.
So, all right. This really, it's very exciting right now, at least. So the word transformer borrows from electrical engineering, where a transformer is a device which converts, uses electromagnetic induction to transfer energy from one circuit to another circuit. This is what they used to name this neural network model, because it transforms an input sentence into an output sentence. So this is the diagram, a picture of a transformer in electrical engineering, converts electricity from this part to this part. So this is how the people working in Google Brain named their architecture. It's a deep neural network architecture, just like RNN and convolutional neural network and so on. And it can transform sentences in one language into another language, which is called machine translation, or it can also transform sentences in one paragraph to sentences in a smaller paragraph, which is called text paraphrasing or summarization. It can also generate text for us and so on. So here are models since ChatGPT 3. We saw ChatGPT in around June 2021, and then there have been so many models, right? In Feb 2023, we have now ChatGPT 4, Alpaca from Stanford, and so on. And every day I can, see a new model coming up from this company or that company. And I'm sure it's going to be like this till we have a little bit of a stabilization in this. All right, so what is a transformer model? This is going to be a little scary if you are not comfortable with neural network architecture or deep neural networks, but we have kept it very, very light in this session. We'll see the coding in coming session. So it's a deep neural network architecture. It was it's nuts and bolts were long in making. In 2015, there was a paper which spoke about attention mechanism, which is the fundamental distinguishing feature of transformer models. And in 2017, we had that landmark paper which spoke about attention. Attention is all you need. Ashish Vaswani and so on. And then this model has, revolutionized our lives. We all know ChatGPT and BERT and Roberta and so on. So not only for NLP, it's also used for computer vision, and it has performed really well in that field also. Like, we have models like DALL-E and all that. So here's the structure of a transformer model. I think I'll not be able to display entire figure in one screen. So we'll go from bottom up. The transformer architecture consists of two blocks. One is called an encoder, other one is called a decoder. Encoder part essentially takes in the input, applies some mathematical operations on it, and generates some representation of the input. That representation is passed on as input to the decoder side of the transformer model. The decoder side also performs some mathematical operations, matrix multiplications on it, and generates some probabilities out of it. And incidentally, these probabilities tell you what is the right translation, or what is the right way to replace the words in input sequence in order to either translate it into a different language, or in order to paraphrase it, or in order to perform any of the NLP question answering. What is the right answer for the question in the input sequence, and so on. So with that, let's have a look at the architecture. Here we put in the inputs to the encoder block of transformer. These inputs are converted into numerical vectors, which are called embeddings, and the transformers use something called positional encoding. That means not just the words, they also take as inputs the positions of those words in a sentence, right? This makes our transformers position invariant. During its operation, the words can get mixed and matched. but it still remembers what was the original position of this word in the sentence when it was fed into the model. So that makes it exceptionally good as compared to models like RNN and LSTM, which do not remember long sequences of input. So after applying positional encodings, we put this more, we feed this input to the first step of our encoder. This is here we can see a split in the input into three pronged fork. So this is a split which is created by multiplying your input with three matrices, three weight matrices, a query weight matrix, a key weight matrix, and a value weight matrix. I'll not be going into the difficult details of it, but there are certain things which must be said. Those three matrices, when multiplied with the input, result in three matrices called Q, K, and V. These matrices are fed as input to this module, which is called attention or multi-headed attention. It is the heart of your transformer model, transformer architecture. This is nothing but a dot product between Q, K, and V. And as a result, a scaled dot product, normalized scaled dot product. That scaled dot product is applied with normalization, and then the result is passed on to a feed-forward neural network, a dense network. Again, some normalization is applied. After this, there can be another encoder block. It can be followed by another encoder block. There can be n encoder blocks. The nx here represents there can be stacked in the stacked fashion. There can be n encoder blocks, and every encoder does the same thing. It applies a multi-headed attention, normalizes the output, passes it on to a feed-forward network, normalizes the output, and then passes it to next encoder, and so on. The last encoder passes out its output to the decoder module, and we will just come to the decoder module in a second. This multi-headed attention here is multiple heads of attention. What is attention? We'll be coming to it in a moment. So multiple heads of attention means we have separate matrices for query, key, and value. Each matrix, each set of matrices composes one attention head. And by having different attention heads, the transformer model can identify different kinds of relationships between the words in an input sequence. For example, we humans, when we look at a sentence, we can identify multiple relationships. A simple relationship is antecedent and precedent, which is the word which follows the current word and which is the word which precedes the word. And then we can have relationship like subject and object. We can also have relationship like similarity. We can have relationships like synonyms and antonyms. So these different kinds of relationships can be captured by multiple attention heads. All these attention heads do their work, identify the kind of relationship they are looking for, and then the final result is concatenated into one vector. It's passed on to the normalization layer, then to the feed-forward layer, and to one more normalization layer. And at the end of final encoder, it's passed on to the decoder. Now let's look at what decoder does. It also has an output embedding layer where the outputs are converted into numbers. It also applies positional encoding. It also applies multi-headed attention, but the very special thing about the first part of your decoder is not just multiple heads of attention, but it's masked attention, which means it uses a special kind of matrix which contains -1s and zeros. The effect of multiplication with this masked matrix is that it blocks off all the words which follow the current word. So your decoder architecture cannot see what is the word that follows the current word. It has access to the previous words, but not to the following words, because in some cases, the entire sentence, if you show to the decoder architecture, it will just learn it, right? It will result in overfitting without actually learning the relationships or patterns between the input and output sequences. So the output of your masked multi-headed attention is normalized and passed on to multi-headed attention, which is just like the encoder block, right? It applies three matrices to input, finds their scaled dot product, applies normalization, passes it to feed-forward neural network, one more layer of normalization. There can be n models, there can be n stacked decoders. At the end of all the decoders, we have a linearization layer and finally softmax. So for all the possible words in the output, in the destination language, for example, if we are talking about machine translation, you get the probability of next word. What is the right word to replace in translation task for the word in input sequence? So what we want to pay attention to here is that this encoder block is exactly what is there in the decoder block, plus this masked multi-head attention. Right. So we have positional encodings, which help the transformers remember the position of words. We have attention mechanism, which enables us to pay attention to a specific words. And what is the benefit of that? The benefit is that it works very, very well with the tasks like translation among languages like English and French, where the word orders are different. The gender specific rules are different in certain languages. Certain words are considered feminine in French, which are considered masculine in English, and so on. So here is this text, and also this diagram is coming from the original paper of 2015, where they were working on the task of machine translation for converting English to French. They used the attention mechanism to identify for converting this English sentence into French when you are working on words, for example, European Economic Zone or European Economic Area. What words in French language should we be focusing on, should we be paying attention to? If you are, for example, translating the words, it should be noted, then what words in French should be paid attention to, and so on. So self-attention is the special type of attention where you don't have the source language and the target language for translation, for example. You are rather looking at the words from one language itself. In the word, you are trying to find out the correct or intended meanings of the words. For example, here we have 3 sentences. I like this pork lane dish. I like this rice dish, and dish out your gifts. So the dish word here means a plate or something in which you serve food to yourself. The dish here means actual edible dish that I would like to eat if it's made of rice. And dish out your gifts here. Dish is a verb which means to give out your gifts freely. The word is dish in all 3 sentences, but the meaning is different in all 3 sentences. And the self-attention mechanism likes to pay attention to the adjoining word. For example, pork lane here tells the model that this dish perhaps does not refer to something edible. It is something on which you serve food. Similarly, rice word here next to the word dish tells it that this is perhaps the edible item. And the word out here next to word dish tells it that this is the verb which means to give away or something like that. So we already discussed the architecture. There are multiple encoder blocks. There are multiple decoder blocks. The encoder block takes in the input sentences, applies encodings to it, computes the attention values, passes those attention values to next layers or next encoders. And finally, the values are taken as input to the decoder module. Finally, the decoder module gives us the probabilities computed by softmax. These probabilities tell you the probabilities of words which you can use to replace or substitute the words in your input sequence. There are also this arrow going from this input line directly to this normalization layer is a skip or residual connection, where some part of your input is going through multi-headed attention, but some part of it is directly fed to the normalization layer. So like ResNets, this is skip residual connections. Same way in this case also. So we have skip residuals in all the decoder and encoder blocks of the transform module. All right, so what are the applications? The applications are in machine translation, computer vision, conversational AI, autocomplete, question answering, search, text generation, summarization. It has huge applications in computational biology also, where they are using it to predict the protein structures and for drug discovery. And how do we use transformer models? You can use Python frameworks like TensorFlow, PyTorch, Keras, and then Hugging Face library for importing pre-trained transformers, ready-made transformers. They have built-in implementations of BERT, ChatGPT-2, then ExcelNet, Roberta, all of them. And some of them we will be using in the session next week. And that's it. I'm done. I'll be looking forward to having you all with me in the 4th and final session, where we'll be doing actually some interesting stuff with transformers.
Oh,
Right.
gotta get up, be ready for the next session. That's a good ending one for this 4-part series. Everyone, please give a round of applause. I want you to flood the chat as a lovely thank you to the amazing Nimrita speaker. She has been phenomenal, and I can only. It's the most comprehensive explanation of all these, and we will be giving the GitHub pages. Oh, there you go. We're flooding with love.
Thank you so much.
Great session. Thanks so much for all these explanations.
Thank you.
And again, thank you to our lovely team, Gagana and Sydney. They have been funneling all those links in the chat. But again, one more round of applause. I know
Thank you
it's
so much.
dinner time for you guys, so please feel free to go back to eating. Oh, look at that. Look at the awesome love in there. And we
Thank you
ended on a
so
good
much.
time today.
Thank you, everyone. Thank you, Aranya. You have been a lovely host today. Thank you, everyone.
Very excited. Thank you so much. We will see you again next week. Follow all the channels for recordings to the previous ones. I guess it's recommended watch the previous ones so that you can be prepared for the fourth and final session next week. And I hope you guys have a lovely day.
Bye-bye. Thank you.
Thank you to all.